Alright, so this is our AP Chemistry lesson video for Chapter 8, and it is Part 1. And so in this video, I'm going to cover Section 8.1 through 8.3. So let's go ahead and get started because we are starting on bonding. Alright, so Section 8.1, we're just going to start talking about bonds as if we've never spoken about them before. But of course, you've already learned about them in Honors Chem. So whenever two atoms or ions are strongly attracted to each other, we say there is a chemical bond between them. There are three general types of chemical bonds. They're ionic, covalent, and metallic. And so, of course, we've talked about all of these. Ionic tend to be between a metal and a nonmetal, and it's a transfer of electrons. Covalent tend to be between two nonmetals, and they share electrons. And metallic are between multiple metals, and they're attracted to each other through the sea of electrons. So let's go back over all of that. So ionic bonds is the electrostatic forces that exist between ions of opposite charge. Ionic bonds normally occur between a metal and a nonmetal. So literally what happens is one gives its electron to another, the one that loses the electron becomes positive, the one that gains the electron becomes negative, and that's when they are attracted to each other and form the ionic bond. A covalent bond results between the sharing of electrons between two atoms. Covalent bonds normally occur between two or more nonmetals. So in this case, both atoms that bump into each other need more electrons, but nobody's willing to give one up. So in that case, they share, and so when they share, that's the bond that forms between them, and it's called covalent. And the metallic bonds are the attractions between the positive nuclei of metal atoms and the sea of electrons. So remember, in metal atoms, the valence electrons can move freely. That's why metals can conduct electricity. And we call that the sea of electrons because they can flow. And so the positive metal nuclei are attracted to just all of the sea of electrons. And so that's what holds metals together. Because normally, if metals were all positive, they would not want to bond with one another. But because of that sea of electrons, that's what keeps them in place. So the electrons involved in chemical bonding are the valence electrons, which are those residing in the outermost occupied shell of an atom. So remember, y'all, valence electrons include the highest energy level, which includes the highest S and P. So like, for example, if something ends in the electron configuration 4s2, 4p1, it has 3 valence electrons because that's the highest S and P. Now, if it just ended in 4s1 and there was no 4p, that would have 1 valence electron. The Lewis symbol for an element consists of the chemical symbol for the element plus a dot for each valence electron. Okay, so for example, beryllium has 2 valence electrons, so for the Lewis symbol, I would just need 2 dots. I wouldn't be interested in any of the core electrons. The number of valence electrons is the same for elements in the same group. So remember, group 1 has 1 valence electron, group 2 has 2. We skip the transition metals. Group 13 has 3, 14 has 4, all the way through group 8, which has group 18, which has 8, except for helium, which only has 2. Because even though it's in group 18, helium only has 2 electrons total, so it can't possibly have 8 valence. So you can tell how many valence by looking at what group it's in. So octet rule. Most elements follow the octet rule, which states that atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons. An octet of electrons consists of full S and P subshells in an atom. So for something to have 8 valence electrons, it would have S2, P6. That's where it gets the 8 from. Elements that do not follow the octet rule include hydrogen and helium. They follow the duet rule. So hydrogen will gain 1 electron to become like helium. Or, of course, a lot of times hydrogen will just lose its electron. Now, there are other elements that don't follow the octet rule, but we'll talk more about those later. So Section 8.2 is on ionic bonding. So an ionic bond involves the transfer of electrons, that should say of, between a cation and an anion. So remember, cation's positive, anion's negative. So the atom is going to give electrons and become a cation, and the other atom is going to accept the electrons and become the anion. The loss of electrons is always an endothermic process, which means it requires energy to take the electron. Okay, remember, we've talked about ionization energy before, energy needed to remove an electron. And the gaining of electrons is generally an exothermic process, which means it releases energy, it is thermodynamically favorable. When ions come together, energy is released, so ionic bonds are, or ionic compounds are stable. Okay, so that attraction of positive and negative, it's a favorable process, so energy is released, and so that's why ionic bonds are very strong. Lattice energy is the energy required to completely separate a mole of a solid ionic compound into its gaseous ions. So if I take sodium chloride and I try to pull the sodium and the chloride ions apart from each other, I'm having to use a certain amount of energy, and that energy is referred to as lattice energy. All lattice energies are large positive values because it takes energy to pull them apart, because remember, they're attracted to each other, indicating the ions are strongly attracted to one another in these solids. But not every ionic compound has the same lattice energy, so we'll talk about how you can tell. So Coulomb's law is as follows. So we looked at this before. So remember, your Q's are your charges and your D is your distance between the two ions. So thus, for a given arrangement of ions, the lattice energy increases as the charges increase. So if I increase these numbers, that will make my energy increase. And as their radii decreases, so the closer they are together, remember, if I divide by a smaller number, that will make my energy larger. If I divide by a larger distance, that will make this number smaller. Okay, so in other words, in order to have a high lattice energy, I want high charge and tiny ions. Okay, so the tinier they are, the closer they are together, that makes it harder to pull them apart. So it says, arrange the following ionic compounds in order of increasing lattice energy. So, y'all, it's easiest to look at charge first. Then if you have two sets that have the same charges, then you can focus on size. All right, so let's do our charges first. So Na is positive 1, F is negative 1, Cs is positive 1, I is negative 1, Ca is positive 2, O is negative 2. All right, so I'm going in increasing order of lattice energy. So we're going from low to high. Okay, and be careful, because on the AP exam, sometimes they might ask you high to low. But you're so used to going low to high, you just do it backwards. All right, so the highest lattice energy is going to be the one with the largest charge. So CaO has the largest charge, so I can go ahead and determine that's the highest. Now these two, they have the same charges. So now I have to focus on size. So Na, if you look at the periodic table, has 3 energy levels. So N equals 3 for Na. F has 2 energy levels. Cs has 6 energy levels. And I has 5 energy levels. All right, now of course when they become ions, those will change slightly. So like when Cs loses its energy, its electron, it will drop down to 5 energy levels. But still, we can see that these are the smaller of the two sets. Okay, Na and F are smaller. So the smaller the ions, the higher the lattice energy. So what's going to be next is actually NaF, because it's smaller. And so then the lowest charge and the biggest ions, so CSI, that would be our lowest energy. All right, so y'all try the next one real quick. So it says, which substance would you expect to have the greatest lattice energy? So y'all try this. I'll assume you paused it and tried it, so let's look at it together. So let's do our charges first. So Mg is positive 2, F is negative, Ca is positive 2, F is negative, Zr is transition, so we don't know the charge, but we know oxygen's negative 2, and there's 2 of them. So we know zirconium has to be positive 4. Okay, so we're picking the one with the greatest lattice energy, so these have the greatest charge. So it's automatically going to be ZrO2. Now, if it had asked us to put them in order like the previous one, then we would have to compare the size of Mg and Ca. So if you look at the periodic table, Mg only has 3 energy levels and Ca has 4. So MgF2 would have the second highest and CaF2 would have the lowest if it asked us to put them all in order, but it didn't. Okay, so always focus on charge first, then if you have any that have the same charge, then you can focus on size. Alright, so ionic bonds and electrons. Most atoms form ionic bonds in order to achieve noble gas configuration. So for example, sodium, this is noble gas configuration, it's Ne, which is neon, and then it has 1 valence electron, which is 3s1. Well, when it becomes positive, it loses the 3s1 electron. So now its electron configuration is similar to neon, so now it's stable. Whereas, for example, chlorine, it has this electron configuration normally, Ne3s2 3p5. So see, it's almost there. It is negative, so once it gains that 3p6, it becomes like argon. So most elements try to do that. Now, not all of them can. Like some of the transition metals, they will not form noble gas configuration. It just depends on what the charge is. So it says predict the ion generally formed by Sr, S, and Al. Well, we don't even have to predict because we've already learned charges in honors chem. So Sr is in group 2, so of course it's going to be positive 2. S is in group 16, so it's going to be negative 2. Al is in group 13, so it's going to be positive 3. So remember, y'all, we learned this already. Your charges go like this. Positive, positive 2, positive 3, plus or minus 4, minus 3, minus 2, minus 1, and 0. Okay? And that's just because of valence electrons. Like if there's 3 valence electrons, it's easier to lose 3 than try to gain 5 more. Okay? We discussed this in honors, so there's no reason to harp on that here. Alright, it says predict the charges on the ions formed when magnesium reacts with nitrogen. Well, again, we don't have to predict because we already know how to do this. So magnesium is in group 2, so it's going to be positive 2. Nitrogen is in group 15, and so all of those are negative 3. Alright, and so if it wanted us to make the compounds, then of course we would cross our charges like that. Okay, it didn't ask that though, it just asked what the charges were. So magnesium would be positive 2, and nitrogen would be negative 3. Alright, so transition metal ions. Since ionization energies increase rapidly for each successive electron removed, okay, we learned about that already when we learned periodic trends, the lattice energies for ionic compounds are generally large enough to compensate for the loss of up to 3 electrons. So that's why most of the time we don't see charges past positive and negative 3. Like we can, but it's just not common. This means that charges above 3 positive are uncommon. But remember, they do still happen. Okay, here's a chart of just some of the ions that can be formed. And so they do still happen, but they're just not as common. So seeing 1s, 2s, and 3s is the most common. Since transition metals have d sublevel electrons, they do not generally form ions that have a noble gas configuration. So that's what I was telling you about a second ago. So when forming ions, transition metals lose the valence shell electrons first. Those are their s electrons, because remember, we always fill in an s sublevel before we hit the d sublevel. Then as many d electrons as are required to reach the charge of the iron. So for example, iron is normally this right here. It's argon, 3ds, and it's what? I don't know what just happened there. 3d6, 4s2. So if it was iron positive 2, we would just remove the 4s2 electrons. Okay, and you have to be careful. Remember, when we're filling them in, we actually fill in 4s2, then 3d6. But remember, I teach you to then rearrange. That way you never forget which ones you're removing. So it would look like this if it was iron with a positive 2 charge. But it can also be positive 3. So in that case, I would need to remove 1 more, and it would become 3d5. And so notice neither of these, because of those d sublevels, are just a noble gas configuration. Alright, so that's why sometimes they can't be like a noble gas. Alright, so section 8.3 is on covalent bonds. So ionic compounds tend to be brittle, have high melting points, are crystalline, and can be cleaved, which means break with a smooth surface. So if you need an example of an ionic compound to help you remember some of these things, just remember salt, NaCl, sodium chloride. All right, you know sodium chloride, you know what it looks like, you know it's a crystalline solid, okay? It doesn't bend if you hit it with a hammer, so it's brittle. Salt has a very high melting point. So having an example sometimes can help you remember properties. Another property is ionic compounds can conduct electricity if molten or aqueous, not when they're in their solid form. So the formation of covalent bonds can be represented using Lewis symbols. So for ionic compounds, we can represent the formula unit just by writing the formula and crossing our charges. But for covalent bonds, Lewis structures are necessary to show the sharing of electrons. So the unpaired electrons are drawn as dots, the bonding electrons are drawn as a dash. Okay, so the dashes are bonds, the lone pairs or unshared electrons are dots. So it says, predict the formula of the stable binary compound formed when nitrogen reacts with fluorine and draw its Lewis structure. So this time they didn't give me the formula. They just told me we have nitrogen and we have fluorine. So let's just start by looking at how many valence electrons they have. All right, so nitrogen is in group 15, so it's going to have 5 valence electrons. Fluorine is in group 17, so it's going to have 7 valence electrons. All right, so fluorine needs one more, but remember, nitrogen's not willing to give one up. So what they're going to do is they're going to share these two. So see, now F has 1, 2, 3, 4, 5, 6, 7, 8, so F is stable, but N has 1, 2, 3, 4, 5, 6, so N's still not there. So then another F will come along, and it also already has 7, so it can share, and then another F can come along. It also has 7, so it can share. So now all our F's have 8, but if you look, nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. So our formula would end up being NF3. All right, so that's how you can tell, is you just keep sharing until everyone's stable. But if we were drawing the Lewis dot structure, we would change these that are shared into bonds. Now some people don't do that, and I have seen questions on the AP exam where they'll just keep the 2 dots like this, but most commonly you need to do bonds. In my class, I expect bonds. If you leave it as dots, I will mark it wrong. But like I said, you can every now and then on AP exams see where they'll leave the bond as dots. So just know if you see dots in between the 2 elements, those are the ones that are shared in the bonds. But like I said, for my class, I expect bonds to be drawn as dashes, like this. Alright, so you try this one, and then we'll look at it together. It says, compare the Lewis symbol for neon with the Lewis structure for methane, which is CH4. In what important way are the electron arrangements about neon and carbon alike, and how are they different? Okay, so pause it, try it, we'll look at it together. So neon is in group 18, so it has 8 valence electrons. Alright, CH4, we'll quickly go back over how to do Lewis dot structure. So you add up your valence, so carbon has 4, hydrogen has 1, but I'm going to multiply it by 4 because there's 4 hydrogens, so I have 8 valence electrons total. Single atoms go in the middle, so I'm going to put carbon in the middle, bond all my hydrogens, start with single bonds, alright, and then check to make sure everybody's stable. Well, remember, hydrogen only needs 2 electrons, so once it has a bond, it's done. So hydrogen has 2, 2, 2, 2, so hydrogen's good to go. Carbon follows octet rule, so it has 2, 4, 6, 8. Remember, there's always 2 electrons in the bond. So we have 8 electrons, we're allowed 8, so there's my Lewis structure. So it says, what about them is the same? Well, what's the same is both of them have an octet. See, neon has 2, 4, 6, 8. Carbon has 2, 4, 6, 8. So they're the same in that they both have an octet. But what's different? Well, neons are non-bonding or lone pairs of electrons, whereas carbons are bonding electrons or being shared. Okay, so that's what's alike and that's what's different. And then here's my answer. They're both alike because they have an octet. They're different because neons are non-bonding and carbons are bonding. So you don't just have to have single bonds. You can have multiple bonds. A single bond consists of 1 pair or 2 electrons. So there's a single bond, 2 electrons. A double bond consists of 2 pairs of electrons. So 2, 4. So 4 electrons. And then a triple bond consists of 3 pairs. So 2, 4, 6 electrons. All right, and so again, if on the AP exam you saw something like this, that is them showing you all 4 electrons are bonding between the 2. That's why they're in the middle. And so it's a double bond, okay, because I know that that might look a little confusing if you're not used to seeing it that way. And in here you won't see it that way because we draw it as bonding. Alright, so bond length. The distance between the nuclei of the atoms involved in a bond is called the bond length for the bond. As a general rule, the distance between the atoms decreases as the number of shared electrons increases. So yeah, all that means is every time they share another electron, they get a little closer together. Okay, so a single bond would be longer than a double bond, which would be longer than a triple bond. Every extra bond pulls them a little closer together, which makes sense because they're attracting to those electrons. Alright, so that is the end of our first video. Hopefully most of this was review from Honors Chem. There shouldn't really have been much new stuff in this video.